Hydroelectric power plant. In a hydroelectric power plant, electricity is produced from water. A dam is built across a large river to hold back the river water and raise its level to form a reservoir. At the bottom of the dam, there is a floodgate. Water flows through the penstock and rotates the turbine. The flowing water rotates the turbine, which is placed at the end of the penstock. The turbine, in turn, rotates the shaft that is connected to the coils of a generator. These coils are placed in between strong magnetic poles. The rotating shaft turns the coil.
Earlier, we saw how an outside force can break an electron away from an atom and start an electron chain reaction, an electric current flow. One way to provide that outside force is by use of a magnet. It was proved with iron filings that a magnet has magnetic lines of force which connect its poles. For simplicity, let's consider the effect of this magnetic field on a single electrically neutral atom. Now, we move the magnet so that the magnetic field strikes the atom, supplying energy which forces an electron to leave its atom and become a free electron. The result is a sort of electron chain reaction. In a substance such as a length of wire, electrons are normally moving in all directions. But when a magnetic field is passed through the wire, several electrons are forced from their atoms and move in one direction. Now, in studying electricity, we're mainly interested in the movement of free electrons. So, for convenience, we'll look only at the action of electrons in the wire. When the magnetic field sweeps down across the wire, electrons move in one direction. When the magnetic field sweeps up across the wire, the electrons move in the opposite direction.
Particles can have a positive charge or a negative charge. Particles with the same charge repel one another. Particles with opposite charges attract one another. This is because charged particles create electric fields. And electric fields exert a force on charged particles. When there is an electric field between 2 points, we say that there is a voltage between them. Voltage can be thought of as the height of a mountain. Rocks at higher elevations can do more damage. The same is true with voltage. The height of the mountain tells you the energy of each falling rock. The total power is the height of the mountain times the number of falling rocks. Similarly, the voltage is the energy of each charged particle. The total power is the voltage times the number of particles. The number of particles is called the current. In a circuit, the charged particles flow through wires. If the wire is cut, the current stops flowing. All wires have charged particles in them. A battery creates an electric field which pushes the charged particles along. With this setup, if one light bulb breaks, all the
Ohm's law is one of the most important laws in all of electronics. It relates current, voltage, and resistance. With Ohm's law, you can do a lot of simple circuit design and analysis, but never memorize Ohm's law. It's very simple to derive, and let's do that now. Let's take a battery that has a voltage V, and we'll connect the plus terminal to a resistor, and we'll connect the negative to the other end of the resistor. So this is negative terminal, positive terminal, resistor R. Let's ask ourselves, what
David Williams here from the Electronic Engineering Technology Department at Okanagan College, and this video is about electrical energy and power. Now, for the most part, I just want you to be able to use and understand the equation for power, which I'm going to give to you right now. Power, electrical power, is equal to the voltage across something times the current that's going through that thing. But before we get into using this equation, I want to talk about a little bit about how I think about energy and power in electric circuits. So to start off with, let's look at 1 volt. What does 1 volt mean? Well, if we break it down into its component units, 1 volt is equal to 1 joule per coulomb. But what does this really mean, 1 joule per coulomb? Well, to understand what 1 joule per coulomb means, I'm going to give a very brief physics lesson here. Let's say we have a positive charge, some amount of positive charge here, charge located here, and this positive charge is stationary, it can't move. So what this positive charge does is it creates an electric field, and this electric field we can represent